Hi and welcome to this tutorial on electron arrangement. In the previous tutorial, we had learned about how electrons are arranged at different energy levels around the nucleus, and we learned about their shells and their subshells and orbitals and the differences between those terms. So we're going to look in even more detail. In this tutorial, we're going to have a look at electron notation and electron configurations too. So it's important that you understand the subshell notation shown in my diagram here. So the red number 1 is the energy level. So it's telling me we're close to the nucleus here. We're very close to the nucleus. We're as close as you can get in terms of the energy level because it's number 1. The yellow is the type of orbital. That is an S. And I know that our S can have a maximum of 2 electrons. Orbital, it doesn't have any other types within it. And the green shows the number of electrons. So this is a full S orbital. Number of electrons. It's a full orbital, but it's also a full subshell because it only has 1 orbital in it. We're going to learn how to create more of a notation so we can take any element and give its electron configuration. So we sometimes have a notation of electrons it's called electron in box or in boxes notation. So with each subshell, we can draw out the electrons in the orbitals, and each box represents 1 orbital. So the electrons are represented by arrows. Remember we said in the previous tutorial, they spin in opposite directions. So we have 1 arrow pointing up and 1 arrow pointing down. And that signifies the 2 electrons we have and their spins. So if we're talking about the notation that we had before, it was the 1s, well 2 because it was full. Then we're going to notify that by 1 arrow pointing up and 1 arrow pointing down, double-headed arrows. That's telling me that it's full and that I've got my 2 spins. So here is the electron configuration in boxes for nitrogen. And I can actually count the number of electrons and check 1, 2, 3, 4, 5, 6, 7 electrons. If I go to my periodic table, I should have an atomic number because the proton number equals the electron number of 7 for nitrogen. And it's going to help us understand our orbitals and our subshells. So here I can see this is my 1s and it's full. And then I'm moving on to my 2s. And I know that my S only has 1 orbital. And then I'm moving on to my P's, so 2p. And there are 6 electrons that I can fit into. I can fit 2 into px, 2 into py, and 2 into pz. But I've only got 3 electrons here. So this is not full. My P level is not full at the moment. But we've got 3 orbitals here. And instead of putting 2 electrons into px, for example, and 1 into py and none into pz, you can see that I've distributed them evenly. I've put 1 into each. Electrons start filling up from the lowest first. So I put them into my 1s first, and then I move up and up and up bit by bit. Okay, so we've got rules to work out electron configurations. In exams, you'll often have to write out the electron configurations of different elements. And they're not going to take you to F, for example, but they may well involve mostly S, P, and sometimes D as well. Well, often D as well. And you can answer the questions by a set number of rules. So there are ways that you can play the game and get really good at this. So electrons will always start filling up at the lowest subshell first. So they're going to fill up the 1s subshell first, then the 2s, then the 2p, so on and so on and so on. So despite the principal number or the quantum number of 4s being larger, 4 is a larger number than 3, you can see it actually fills before the 3d. So there's a few rules that you just need to remember. There's a few exceptions to the rule that you just need to remember. So that rule is overridden, and it's overridden by the lower energy number of the 4s, meaning it's filled first. So we're going to fill 3s, then 3p, then 4s, then 3d, then 4p. Okay, that's our exception that we need to learn. So have a think about the notation before I fill this in. So can you fill this in yourself? So pause the video and give it a go. Let's look at helium. So you're going to need your periodic table for this. So helium's got 2 electrons, and there's only 1 S subshell in shell 1. So the total number of electrons I can get from the periodic table, it tells me there's 2. And therefore, it's going to fill the 1s subshell first, and that leaves it full. So the notation is going to be 1s2. That's showing me how many electrons, that number. Lithium's got 3 electrons, so we're going to fill the 1s first. So 1s2, and then we're going to move on to the next energy level, so 2s. And that's going to have a maximum of 2, but we've only got 3 electrons. We've used 2 up already, so we're going to put the remaining 1 in there. Then we've got nitrogen, which is 7 electrons. So we're going to fill the 1s. You see there's a pattern here. Then we're going to fill the 2s, and the 2s is full, so it's 2s2. Then the next energy level is 2p. So I'm thinking I've got 7 electrons in total. I've used 4 so far, and I've got 3 left. So it's going to be 3 electrons going into the p. What about calcium? Now that's got a lot more, so it's a little bit more to think about. So 1s, 2s is going to be filled. The 2p is going to be filled. Remember, there's 6 maximum in there. Now, the second shell has only got s and p, so I'm going to have to jump to my third shell. That's going to have s, that's going to have p, and that's also going to have d. But remember the exception. 4s fills before 3d. So the next one is actually going to be 4s. And so far I've used 18 electrons, 2 plus 2 plus 6 plus 2 plus 6. I've got 2 left, so we're going to have a full 4s. So that's the exception. Some students will write 3p6, they'll get to here, and they'll jump straight onto 3d2. That's incorrect, because we've got to remember that once we get up to these higher energy levels, the 4s fills before the 3d. So we don't fill the 3d at all yet. Here's a summary where you can read a little bit more information as to sort of my process, and so pause the video and have a look at that if you want a bit more of an explanation. You'll have noticed when I gave you the nitrogen example earlier on that electrons fill each orbital in each shell individually before they start pairing up. So I put 1 electron in px, 1 electron in py, 1 electron in pz before I paired them up. So when we fill orbitals in a particular subshell, we try to avoid having pairs of orbitals, okay? This is because having 2 electrons in a single orbital requires more energy. They repel each other. So for the p's, I showed them like that, rather for px, py, and pz than doing this with my 3 electrons, okay? That is frowned upon because these 2 are going to repel, and they are much happier being in their individuals first, so they don't repel before we pair them up. Here's a better example of my diagram, okay? So with nitrogen, it's going to put 1 electron in py, 1 in pz, and 1 in px, and then you pair them up as you move on to the future elements. This is going to be really, really unlikely. So here we've got no electron repulsion because each individual electron is in a different orbital. Here, we've got electron repulsion, which we're going to try and avoid. We can't always avoid it, but if we can, we do, because it's lower energy, and things will always try and be in a lower energy state. So this is incorrect. And this one is correct. Just a note on free radicals. So free radicals are atoms, molecules, or ions that have unpaired electrons in their outer shell configuration. So imagine we've got 3 floors of a house and we've got 7 guests coming to visit. So we're doing nitrogen here. Floors 1s and 2s have 1 room each, okay? Whilst floor 2p's got 3 rooms. Each room can contain a maximum of 2 guests. So we fill up floor by floor. So when we reach floor 2p, we would rather give each guest their own individual room than to pair them up and put a pair of guests in one room, one in the next, and no one in the third room. Understandably, each guest would rather probably have their own room, the 3 of them. So when drawing orbital diagrams, remember to draw the electron arrows pointing in opposite directions as well. So you would have seen in the previous image that 1 points up and 1 points down. We can also consider electron configurations of ions. So to find the electron configuration of ions from either the S and P block of the periodic tables, there's my S and there's my P, electrons are eliminated from or added to the subshell with the highest energy level. We don't touch the lower energy levels. We only mess around with the higher energy levels. So how do you find the electron configuration of an ion? So pause the video and have a think. Let's have a look at some examples then. We've got calcium and fluorine. So these can both form ions. So let's have a look at how we notify those in electronic configuration. So calcium forms a positive ion. 2 electrons are removed. It's in group 2, so we're going to remove 2 electrons. And they're going to be removed from the 4s subshell because that's the highest energy level. So if I write out the configuration of just normal calcium, the atom, it's going to be 1s2, 2s2, 2p6, 3s2, 3p6, and remember, the 4s fills before the 3d, so 4s2. There we go, that's normal calcium. So just Ca. If I'm looking at Ca2+, I know that 2 electrons are removed from the outer shell. So everything is going to be the same down here. We do not remove electrons from the lower energy levels. We are just going to remove those final 2 electrons. And so there is nothing. That is our configuration of my ion. What about with fluorine? So fluorine gains electrons, doesn't it? So it's got 7 in its outer shell. It wants to gain 1 to get its 8. So if we've got fluorine, we're going to have its configuration is going to be 1s2, 2s2, 2p5. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So we've got 7 electrons in the outermost shell, don't we? In the p. And if we've got a fluorine ion, that's going to be F-. We are going to add an electron. And we're not going to add any electrons lower down. We can't, they're full. They want the S's. So then we're going to get to 2p and we're going to add an electron. So it's going to become 2p6 instead of 5. So there's my configuration of my fluorine ion. So in some textbooks, you might find people using shortcuts because they don't want to have to write out 1s2, 2s2, 2p, because it's a given that those won't change. So they use a shortcut with noble gases. So you might see a symbol such as AR in brackets, and then they continue the configuration on from that point. So it's shorthand. It's shorthand for writing the electron configuration of AR. So if you see AR, what that represents is 1s2, 2s2, 2p6, 3s2, 3p6. So rather than write all of that, someone just might shorthand that. They mean the same thing. Okay, so potassium, for example, can be written as a really, really long-winded. So if we change this and make it potassium. So let's make that potassium. We could write all of this out and then at the end add in whatever makes it actually potassium, so 4s1. Or we could just be much, much quicker and write AR in brackets. That accounts for all of this part here. And then all we need to do is write 4s1. And that is potassium's electron configuration. Just to explain that a half full or a full 3D subshell is especially stable. And this is relevant for transition metals, which you probably won't touch on till year 13, but it is still worth knowing. So chromium and copper, they've got unusual properties as their subshells fill differently. So chromium and copper donate their 4s electrons to the 3D subshell. And that means that the 3D subshell is either full or half full, just because that's electronically more stable. Now, don't panic too much about this, because this is something that you actually pick up in more detail and you'll understand better when you study transition metals. It's really pulled out quite clearly in the specification. But if we actually write out, so our expected configuration of chromium, if we're using the rules that we've learnt, would be 1s2, 2s2, 2p6. You can see why people like to use the shortcuts, because this can take a long time. Always use the full in the exam, unless you're told otherwise, 3d4. Now the actual is 1s2, 2s2, 2p6, 3s2, 4s1, 3d5. D can have 10 electrons, so 5 is half full, and that is more desirable than it being 4s2, 3d4. That is not half or full, is it? 4, weird number. So one of the electrons in the 4s is going to get donated, and that's going to make that 3d nice and half full. 1, 2, 3. So that means that one guest has gone into each room, and that is much better. Okay, and for copper, it's quite similar. If I just give you the end of it, it's going to be 3p6, 4s2, 3d9. Now 9, not great. So what we're going to end up with is, if I just carry on from the 4s, from the 3p, it's going to be 3p6, 4s1, 3d10. And what that means is they're going to pair up nicely now to fill all 10. So this is full, this is half full, it's more stable. So these are correct, these are incorrect. When forming ions, they're going to lose the 4s electrons before the 3d. Okay, so that's a bit of a trick you need to learn. So usually when atoms form ions, they lose their electrons from the 3d subshell first. It's the higher energy level. But actually it's the opposite when they lose them. So they're going to gain them into the 3d first, but they're going to lose them from the 4s first in transition elements. So again, if we have a look at what that looks like here, we are going to have, our charge is going to be 0, obviously on a chromium atom, and it's going to be 3 on a 3+. And so we're going to have 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. That's what we agreed because it's half full, it's more stable with the 3d. But when we lose electrons, have a look at this. So it's going to be 1s2, 2s2, 2p6. So we don't lose any of them down here. So this is all going to be the same, 3p6. But we're going to lose our 4s first, and then we're going to lose 2 from our 3d, which is going to leave us with 3d3 left over. So some students might instead write the ending as 4s1, 3d2. That is incorrect. We lose them from the 4s first.